Imagine a force so powerful it could wipe out every credit card on Earth from halfway across the galaxy. A single teaspoon of its magnetic field would weigh as much as a battleship. This isn't science fiction, it's the reality of magnetars, cosmic monsters lurking in the darkness of space, capable of violence beyond anything else in the universe. These neutron stars are the universe's ultimate oddballs, born from the ashes of supernova, yet so bizarre, they defy everything we know about physics. Their magnetic fields are a quadrillion times stronger than Earth's. Their surfaces crack under unimaginable pressure, and when they snap, they unleash explosions called starquakes so bright they outshine entire galaxies for milliseconds. But here's the real mystery: how do these terrifying objects even come to exist? For decades, scientists have wrestled with this question, proposing wild, brilliant, and sometimes contradictory theories about their origins. Some believe magnetars are born from the most chaotic stellar deaths imaginable, while others argue they're the result of cosmic cannibalism, stars devouring their own siblings. There are theories involving exotic states of matter that shouldn't exist, collisions that defy logic, and even hints that magnetars might hold the key to understanding dark matter itself. Today, we're diving into 30 of the most fascinating explanations for these cosmic anomalies. From the widely accepted to the downright speculative, we'll explore how a dying star can transform into something this extreme. You'll hear about theories involving runaway dynamos, quantum weirdness, and stellar mergers so violent they bend spacetime itself. Some ideas might sound like they're straight out of a superhero comic. Others will make you question everything you thought you knew about how the universe works. So buckle up. By the end of this journey, you won't just understand magnetars better, you'll see the universe itself in a whole new light. The most widely accepted explanation for magnetars starts with the violent death of a massive star, a supernova so powerful it rips apart entire solar systems. When a star at least 8 times heavier than our Sun exhausts its nuclear fuel, the core collapses in milliseconds, crushing matter into a neutron star so dense, a sugar cube of its material would weigh as much as Mount Everest. But in rare cases, this collapse doesn't just create an ordinary neutron star, it births something far stranger. Here's where physics gets wild. As the core implodes, it doesn't just shrink, it spins faster, like a figure skater pulling in their arms. This sudden acceleration, combined with chaotic currents of ultra-hot plasma swirling inside the newborn neutron star, could act like a cosmic dynamo, twisting and amplifying magnetic fields to mind-bending levels. Picture a runaway electric generator, but instead of copper wires, it's made of spinning neutron soup threaded with magnetic forces a quadrillion times stronger than Earth. Some simulations suggest the star's outer layers might slam into the collapsing core like a hammer, stirring the material into a frenzy. Others propose that quantum effects in the neutron star's core, where protons and electrons merge into bizarre superfluid states, could lock magnetic fields into place like cosmic flywheels. The result, a magnetar where the magnetic field isn't just strong, it's practically alive, crackling with energy, waiting to unleash devastation across light years. Yet mysteries remain. Why do only 1 in 10 supernova produce magnetars? Could it depend on the star's initial spin or the angle of its collapse? Some researchers even speculate that the loudest supernova, the ones that outshine their galaxies, might be magnetars announcing their birth with a magnetic scream. Whatever the answer, this theory proves one thing: when stars die, they don't always go quietly. Sometimes they leave behind monsters. But what if ordinary supernova aren't violent enough to explain the most extreme magnetars? Enter hypernova, cosmic detonations so powerful they make typical star deaths look like firecrackers. These rare eruptions occur when stars at least 30 times more massive than our Sun reach their violent end. Unlike standard supernova, which leave behind neutron stars, hypernova unleash so much energy they can forge something far stranger. The difference lies in the collapse. During a hypernova, the star's core doesn't just implode, it completely shatters, ejecting jets of plasma at nearly the speed of light. These jets act like cosmic blowtorches, heating the surrounding material to unimaginable temperatures and stirring it into a magnetic maelstrom. As the core contracts, this swirling chaos could amplify magnetic fields to levels even a typical neutron star couldn't sustain. Imagine stirring a cup of tea with a spoon. Now replace the spoon with a tornado and the tea with a superheated nuclear plasma threaded with magnetic fields. That's the kind of turbulence we're talking about. There's another twist. Some hypernova might be paired with long gamma-ray bursts, the brightest explosions in the universe since the Big Bang. These bursts could act like cosmic lightning rods, channeling energy directly into the newborn Magnetar's magnetic field. In this scenario, the star isn't just born with extreme magnetism, it's practically baptized in it, emerging from the explosion like a phoenix wrapped in chains of pure magnetic force. But here's where things get controversial. Not all hypernova leave behind magnetars, and not all magnetars seem to come from hypernova. Some researchers argue it's not just about the explosion's power, it's about the star's rotation. A fast-spinning progenitor star could transfer its angular momentum to the collapsing core, turning it into a magnetic dynamo on steroids. Others suggest binary systems might play a role where two massive stars orbit each other before one explodes, twisting magnetic fields like cosmic taffy in the process. One thing's certain, if hypernova really are the cradle of the most extreme magnetars, they're proof that the universe has a flair for the dramatic. These aren't just stars dying, they're stars going out with a bang so loud it echoes across the fabric of spacetime itself. Now picture this cosmic catastrophe, two dead stars, each already crushed into spheres just 12 miles wide but weighing twice as much as our sun, locked in a fatal dance. As they spiral closer, their immense gravity distorts spacetime itself, sending out ripples we can detect as gravitational waves. In the final moments, they collide with the energy of a billion supernova, and in that apocalyptic merger, something extraordinary might be born, a magnetar. This isn't just theoretical. Computer simulations show that when neutron stars merge, the resulting object can become a swirling, hypermassive neutron star, a temporary monster with a magnetic field amplified beyond comprehension. Think of it like blending two hyperactive dynamos together. The original stars might have had strong magnetic fields individually, but their collision stirs those fields into something far more extreme, like combining two whirlpools into a single planet-swallowing vortex. The key lies in the chaos of the merger. As the two neutron stars shred each other apart, their cores, already made of the most exotic matter in the universe, get stretched, spun, and superheated. Quantum particles called magnetic flux tubes, normally buried deep inside, get yanked to the surface where they tangle and snap like cosmic rubber bands. This process, known as magnetic reconnection, could unleash a storm of energy so intense it turbocharges the newborn star's magnetic field in milliseconds. Some models suggest the remnant might spin hundreds of times per second at first, turning it into a magnetic powerhouse before slowly settling into the steady, lethal hum of a mature magnetar. But there's a catch. Most neutron star mergers are thought to collapse quickly into black holes, leaving no remnant behind. So why would some survive as magnetars? The answer might hinge on mass. If the combined weight of the two stars is just below the threshold for immediate collapse, the merged object could linger, spinning wildly, its magnetic field intensifying until it stabilizes into one of these cosmic anomalies. Even more intriguing, we might have already witnessed this process. The gravitational wave event known as G2019, detected in 2019, produced a mysterious flash of light some astronomers believe could have come from a newborn magnetar. If true, it would mean these ultramagnetic beasts aren't just born from solitary supernova. They might also arise from the most violent stellar collisions in the universe. Yet mysteries linger. Why do some mergers produce magnetars while others vanish into black holes? Could the star's original magnetic fields or spin directions determine the outcome? And if these events really do forge magnetars, why are they so rare compared to other neutron stars? Each question pulls us deeper into the enigma of these cosmic monsters, reminders that even in death, stars can create something stranger than fiction. Deep inside a newborn neutron star, chaos reigns. A seething ocean of protons, neutrons, and electrons crushed to near breaking point by gravity swirls in turbulent currents hotter than the core of the sun. This isn't just random motion, it's a cosmic power plant, one that might hold the key to magnetar formation. The dynamo theory suggests these frenzied plasma flows don't just carry heat, they twist and stretch magnetic fields like taffy, amplifying them to impossible extremes. Think of it like this. Imagine stirring a cup of coffee with a spoon. The liquid starts to rotate, creating a tiny whirlpool. Now replace the coffee with a superfluid nuclear plasma 1 trillion times denser than steel, and the spoon with the neutron star's own mind-bending rotation spinning hundreds of times per second. Every twist and turn wraps magnetic field lines tighter, pumping energy into them like a runaway generator. In ordinary stars, this process creates modest magnetic fields. But in neutron stars, where matter behaves unlike anything on Earth, the effect becomes explosive. Here's where it gets wild. The dynamo doesn't just amplify existing fields, it can create them from scratch. Quantum fluctuations in the star's ultra-dense core might produce tiny magnetic seeds. As these seeds get caught in the plasma's turbulent currents, they're stretched and folded like cosmic origami, growing exponentially stronger with each rotation. Some models suggest that in just 10 seconds, this process can transform a weak magnetic whisper into a roar loud enough to rip atoms apart across interstellar space. But dynamos don't work the same way for every neutron star. The star's initial spin rate is crucial, too slow, and the plasma doesn't stir vigorously enough to amplify fields dramatically. Too fast, and the star might tear itself apart before the dynamo can finish its work. Temperature also plays a role. Cooler regions allow magnetic fields to freeze into the plasma, locking in their amplified strength, while hotter zones keep fields fluid and dynamic. There's another twist: convection. As the neutron star cools in its first few minutes, hotter material rises while cooler sinks, creating colossal updrafts that act like magnetic elevators. These currents can transport amplified fields from the core to the surface, where they suddenly emerge as the star's devastating external magnetism. It's as if the star has hidden a monstrous electromagnet beneath its crust, only to reveal it once the dynamo's work is done. Yet the dynamo theory isn't perfect. Some magnetars show magnetic fields aligned with their spin axes, while others have fields tilted at odd angles, something basic dynamo models struggle to explain. And why do some neutron stars with similar spins and masses end up as ordinary pulsars, while others become magnetars? The answer might lie in tiny initial differences. A slightly faster birth spin, a marginally more turbulent collapse that cascade into cosmic divergence. What's undeniable is this: if the dynamo theory holds, it means every magnetar is a masterpiece of chaos. A stellar Rube Goldberg machine where gravity, quantum physics, and fluid dynamics conspire to create something far greater than the sum of its parts. And somewhere in that chaos, the universe scribbles its most powerful magnetic signatures we're only beginning to decode. What if magnetars aren't the end of the line but a cosmic stepping stone? There's a radical theory suggesting these ultramagnetic monsters might actually be neutron stars caught mid-transformation, morphing into something even stranger: quark stars. This hypothetical state of matter could rewrite the rules of magnetism itself, cranking ordinary neutron star fields up to nightmarish levels. Picture a neutron star's core under unimaginable pressure where even the laws of particle physics start to break down. Normally, neutrons stay intact, packed like marbles in the star's interior, but under extreme conditions they might shatter into their constituent parts, quarks. These fundamental particles, normally forever bound inside protons and neutrons, could suddenly find themselves swimming freely in a bizarre quantum soup. And this transition from neutron matter to quark matter might be the secret behind Magnetar's absurd magnetic power. Here's why this matters. In a quark star, freed up and down quarks could reorganize into exotic configurations, like superconducting strange quark pairs that carry current with zero resistance. With no friction to sap their energy, these currents could generate magnetic fields dwarfing anything in a conventional neutron star. It's like comparing a refrigerator magnet to the particle beams inside the Large Hadron Collider. The transition itself could be catastrophic. As the neutron star's core fractures into quarks, it might release pent-up energy in violent starquakes explosions we've detected from magnetars. These quakes could then jolt the star's crust, twisting magnetic field lines like a cosmic taffy pull. Some models suggest the process might even create temporary magnetic bubbles, regions where the field strength spikes briefly to 100 times normal before settling into a magnetar's steady roar. Yet quark stars remain purely theoretical. No telescope has definitively spotted one, and the mathematics describing them makes black holes look simple. If they do exist, they'd be the densest stable objects in the universe, so compact, a teaspoon of quark matter might outweigh all the cars on Earth. Their surfaces could be smoother than any neutron stars, their interiors so alien that light itself might behave differently inside them. The biggest clue might come from Magnetar spin rates. Quark stars should rotate slower than neutron stars. Their more rigid interiors would break their spin faster. Intriguingly, some magnetars do show unexpectedly sluggish rotation, as if something inside them is putting the brakes on. Other potential signatures include unique neutrino emissions during the quark transition phase, or gravitational waves with telltale frequency shifts as the star's core rearranges itself. Skeptics argue there's no hard evidence quark stars exist at all, but supporters counter that magnetars might be that evidence. After all, if you needed a natural particle accelerator to create quark matter, where better to look than the corpse of a supernova, where pressures eclipse anything we can recreate on Earth? Whether this theory holds or not, it forces us to confront a thrilling possibility, that magnetars aren't just dead stars but cosmic laboratories forging states of matter so extreme they redefine what matter even means. Here's a mind-bending possibility. What if magnetars aren't powered by ordinary physics at all, but by particles so exotic they shouldn't exist? Enter magnetic monopoles, hypothetical relics from the universe's first second, carrying a single magnetic charge instead of the usual north and south pair. While no experiment has ever detected one, their theoretical existence could rewrite the story of magnetar formation in the strangest way imaginable. Picture the early universe, a seething quantum foam where symmetry ruled. In those chaotic first moments, theorists suggest monopoles may have formed as cosmic defects like cracks in frozen ice. Most would have annihilated or diluted as the universe expanded, but a few, drifting through space for billions of years, might have found their ultimate trap: neutron stars. These ultra-dense objects act like gravitational sponges, soaking up stray particles. As monopoles rain down onto a neutron star's surface, their unique properties could trigger a magnetic apocalypse. Unlike ordinary particles, monopoles wouldn't cancel each other out, they'd stack. Imagine pouring magnets into a box, but instead of pairs sticking together, every single one adds its charge. In a neutron star's core, this stacking effect could escalate wildly. quantum calculations suggest that just one monopole per 10 billion protons might be enough to amplify the star's magnetic field to Magnetar levels. The star's ridiculous density does the rest, squeezing these particles so close together, their combined fields merge into a single, continent-sized magnet of doom. But there's a catch: monopoles wouldn't just sit there. Some models suggest they'd catalyze proton decay, converting the star's matter into energy and exotic particles in a runaway reaction. This process could explain Magnetar flares, sudden bursts where the star vomits pent-up magnetic energy like a cosmic pressure valve. It's as if the star becomes a battery, charging itself on monopole annihilation until it can't hold another drop. The wildest twist: monopole-rich magnetars might not even look like neutron stars anymore. Their cores could crystallize into bizarre magnetic lattices, or even transition into entirely new states of matter. Some theorists propose that certain gamma-ray flashes, mysterious millisecond bursts with no obvious source, could actually be the dying screams of monopoles inside these stars. Of course, this is all speculation piled atop hypothesis. No one's ever seen a monopole, and many physicists doubt they exist at all. But if they do, and if they're lurking in magnetars, it would mean these cosmic monsters aren't just dead stars. They're museums preserving the universe's most elusive particles in the most violent way possible. And that raises an even stranger question: could monopoles be the dark matter we've been searching for all along? If so, magnetars might not just be magnetic freaks, they could be cosmic Rosetta Stones, hiding secrets about everything from quantum gravity to the birth of spacetime itself. Most stars don't start off magnetic, but some are born rebels. Imagine a massive star, not just any star, but one twisted by internal dynamos so fierce, its surface writhes with magnetic loops powerful enough to rip apart planets. When this stellar titan dies, its magnetic legacy doesn't just vanish. It gets compressed, supercharged, and reborn in the collapsing core. This is the primordial field theory, where magnetars might owe their absurd magnetism not to their own turbulent birth, but to the cosmic inheritance left behind by their equally bizarre parents. The math behind this is staggering. A massive star's magnetic field, already thousands of times stronger than the sun's, gets concentrated as the core collapses. Picture squeezing a bar magnet into a sphere the size of Manhattan. The field lines don't disappear, they pack tighter, amplifying exponentially. During a supernova, this compression could crank an already intense field into the Magnetar range. Some simulations suggest a progenitor star with just a 1% magnetic energy boost, barely noticeable during its lifetime, might birth a neutron star with a field 1,000 times stronger than average. But why would some stars have these freakishly strong fields to begin with? One clue lies in stellar mergers. If two stars in a binary system spiral together, their tangled magnetic fields could merge into a chaotic knot, creating a Frankenstein star with magnetism dialed up to 11. Another possibility involves turbulent convection in massive stars' cores, regions where plasma currents act like gargantuan electrical coils, generating self-sustaining magnetic loops. These fossil fields, trapped beneath the star's surface for millions of years, might only reveal their true power in death. Observations back this up. Astronomers have spotted a handful of magnetic massive stars in our galaxy, blue giants with surface fields strong enough to distort their own stellar winds. When these stars eventually explode, their neutron star remnants should, in theory, become magnetars. Intriguingly, the predicted numbers roughly match how many magnetars we've detected. Yet there's a twist. Not all magnetic massive stars seem to produce magnetars, and not all magnetars appear to come from magnetic progenitors. Some researchers argue the star's rotation plays a critical role. Only if the core retains enough spin during collapse can it preserve and amplify the primordial field. Others speculate that certain stellar compositions like metals in the outer layers might act as magnetic insulators, preventing the field from leaking away before the supernova. The most tantalizing evidence comes from star clusters. Magnetars found in young stellar nurseries, regions where massive stars live fast and die young, tend to have stronger fields than those in older neighborhoods. This fits the primordial theory perfectly. Stars in these clusters are born from magnetically rich gas clouds, passing that gift down through generations. What makes this idea so compelling is its simplicity. Magnetars don't need exotic physics or freak collisions. They might just be the universe's way of recycling magnetic energy on the most extreme scales. It's a cosmic family heirloom passed from star to stellar corpse, proving that sometimes the most violent objects in space owe their power to the quiet legacies of their ancestors. At the heart of every newborn neutron star, there's a battle between order and chaos, and in the case of magnetars, chaos might be winning. Differential rotation sheer takes the spotlight in this cosmic drama, where different layers of the star spin at wildly mismatched speeds, twisting magnetic fields like a pretzel until they reach impossible strength. Think of it like dragging a spoon through honey. The outer layers move faster than the sticky center, creating turbulent swirls. Now imagine that honey is a 12-mile-wide ball of nuclear matter spinning hundreds of times per second, and the spoon is the neutron star's own gravity warping spacetime. As the star's crust and core rotate at different speeds, magnetic field lines threading through them get stretched and tangled like cosmic spaghetti. Every twist pumps more energy into the field, amplifying it exponentially in a process called the omega effect, where omega represents the sheer violence of this rotational mismatch. Here's where it gets extreme. In ordinary neutron stars, this differential rotation smooths out within minutes as the star settles into a unified spin. But in magnetars, something keeps the chaos alive. Quantum effects in the superfluid core might create frictionless vortices that resist synchronization, or the star's crust could fracture under the strain, creating seismic waves that keep stirring the magnetic pot. Some models suggest the differential rotation might persist for hours, an eternity in neutron star time, long enough to crank the magnetic field from merely intense to downright apocalyptic. The numbers defy intuition. Just a 1% difference in rotation rates between the core and surface could, over thousands of rapid spins, amplify a magnetic field a billionfold. Picture a dynamo where every rotation doesn't just add energy, it multiplies it, wrapping field lines into knotted coils so dense they start influencing the star's very structure. Simulations show these fields can grow so strong, they literally push back against the star's rotation, slamming the brakes on some layers while accelerating others, a feedback loop of magnetic fury. Yet mysteries linger. Why don't all neutron stars experience this runaway amplification? The answer might lie in the star's birth spin. Stars born rotating too slowly lack the rotational energy to sustain the turbulence, while those spinning too fast might tear apart before the process completes. There's also the wild card of magnetic reconnection, when twisted field lines snap and rearrange, releasing energy in bursts that could either amplify the field further or destabilize it entirely. Astronomers have spotted potential smoking guns. Some young neutron stars show glitches, sudden spin changes thought to be caused by interior adjustments. Magnetar glitches tend to be more violent, as if something deep inside is constantly rearranging itself. Then there's the case of SGR 0418+5729, a magnetar whose X-ray pulses suggest a surface rotating slower than its core, a telltale sign of differential rotation freezing magnetic fields into place like a cosmic flywheel. This theory paints magnetars not as static monsters, but as evolving entities, their magnetic fields forged in the ongoing struggle between rotation and resistance. It's a reminder that even in the coldest corners of the universe, motion breeds magnetism, and sometimes that magnetism becomes a force beyond reckoning. Sometimes the universe amplifies chaos in ways that defy intuition. Magnetorotational instability is one of those cosmic feedback loops, where a star's rotation doesn't just interact with its magnetic field, but becomes locked in a self-destructive dance that spirals out of control. Picture a spinning top wobbling violently as it loses speed, except this top weighs more than the sun and is wrapped in magnetic fields strong enough to shred atoms. The instability begins with a simple mismatch. In a newborn neutron star, the outer layers might rotate faster than the deeper core, creating shear forces that twist magnetic field lines like rubber bands. Normally, these forces would even out over time, but under extreme conditions, something far stranger happens. The twisting fields themselves begin to influence the star's rotation, creating turbulence that further tangles the magnetism, which then amplifies the turbulence even more. It's a vicious cycle where every turn cranks the system closer to chaos. Astrophysical simulations reveal just how explosive this process can be. Supercomputer models show that in mere seconds, magnetorotational instability can stretch weak seed fields into monstrous coils, wrapping around the star like a cage of lightning. The magnetic pressure grows so intense it starts pushing back against the star's own gravity, distorting its shape into a wobbly, asymmetrical nightmare. Some calculations suggest the fields can grow 10 trillion times stronger than Earth's before the system finally stabilizes or collapses entirely. What's fascinating is how delicate the balance can be. For this instability to trigger, the star needs just the right blend of spin and internal structure. Too rigid, and the differential rotation smooths out harmlessly. Too fluid, and the star tears itself apart before the fields amplify. But in that narrow sweet spot, where the core resists motion like molasses while the outer layers whip around at relativistic speeds, the instability takes hold, transforming an ordinary neutron star into a magnetar through sheer rotational violence. The aftermath is even wilder. As the instability peaks, the star's crust buckles under the magnetic stress, launching starquakes that ripple across its surface. These quakes release energy in bursts so bright, they can outshine entire galaxies for a fraction of a second. Meanwhile, the magnetic fields, now twisted into impossible knots, begin reconnecting, snapping like cosmic elastic bands and converting their pent-up energy into blistering radiation. Yet mysteries linger. Why do some neutron stars experience this runaway instability while others don't? Simulations hint that tiny initial differences like the angle of the star's spin axis or the presence of even minor magnetic fields at birth might tip the scales. Others suggest that external factors like debris falling back onto the star after a supernova could stir the turbulence needed to ignite the instability. What's clear is this: magnetorotational instability doesn't just amplify magnetic fields, it weaponizes them. It turns a star's own rotation against itself, forging cosmic monsters in a crucible of chaos. And if the simulations are right, it might be one of the universe's most efficient factories for the most magnetic objects in existence. What if magnetars aren't just cosmic accidents, but dark matter detectors? One of the most speculative and tantalizing theories suggests these ultramagnetic monsters might be hoarding invisible particles from the shadow universe. Dark matter, that mysterious substance outweighing normal matter 5-to-1, could be lurking inside neutron stars, subtly warping their magnetic fields into something far more extreme. The math behind this is eerily persuasive. Neutron stars, with their ridiculous gravity, act like dark matter vacuum cleaners. Over millions of years, they could accumulate vast quantities of these ghostly particles, especially weakly interacting massive particles, or WIMP. Normally, WIMP pass through ordinary matter like phantoms, but inside a neutron star's core, where densities eclipse anything else in the universe, even dark matter might get trapped. Some calculations suggest a single neutron star could capture enough WIMP to form a dense, smoldering dark matter core within its heart. Here's where things get bizarre. If enough dark matter clusters in the star's center, it might start influencing the neutron soup surrounding it. Certain WIMP models predict these particles could interact with quarks in ways that alter the star's conductivity, essentially turning its core into a superconductor on cosmic steroids. Picture a planet-sized electromagnet where dark matter subtly tweaks the dials, allowing magnetic fields to grow stronger and more organized than normal physics permits. There's an even wilder possibility: dark matter annihilation. If WIMP collide and destroy each other inside the star, they'd release energy that could stir the neutron fluid like a spoon in molten metal. This turbulent motion might amplify magnetic fields through a dark matter-powered dynamo effect, one where the fuel isn't rotation or heat, but the slow burn of invisible particles meeting their end. Some theorists estimate this process could inject enough energy over millennia to push a neutron star's magnetic field into Magnetar territory. Observational clues are scarce but intriguing. A handful of Magnetars exhibit glitches where their spin suddenly changes behavior that doesn't always fit conventional models. If dark matter occasionally collapses or redistributes inside the star, it could explain these anomalies by subtly altering the star's moment of inertia. Even more provocative are certain gamma-ray bursts from magnetars that show unexpected spectral lines hinting at energy releases that don't quite match known particle interactions. Of course, this remains fringe science. No one's ever directly detected dark matter, let alone confirmed it can accumulate in neutron stars. Critics argue neutron stars already have enough exotic physics without invoking invisible particles. But supporters counter that if dark matter exists and everything suggests it does, then neutron stars are nature's perfect traps for it. And if that's true, magnetars might not just be magnetic freaks. They could be the universe's most extreme dark matter laboratories, broadcasting secrets about the invisible cosmos every time their surfaces crack under magnetic strain. Whether this theory holds or not, it stretches our imagination, forcing us to consider that the most violent objects in space might be shaped by the most elusive substance in existence. And if future telescopes catch a magnetar flaring in ways that defy all standard models, we might just have dark matter to thank. Now consider the universe not just as a collection of stars and galaxies, but as a fabric, one that might have rips and tears from the moment of its birth. Cosmic strings, hypothetical scars left over from the Big Bang, could be threading through space like invisible wires, thinner than a proton but denser than a mountain range. If these space-time defects exist, they might play the ultimate cosmic prank, turning ordinary neutron stars into magnetars through gravitational sabotage. The concept sounds like pure science fiction, but the math holds startling potential. Cosmic strings, if real, would carry unimaginable tension. Some models suggest just 1 centimeter of string could weigh 1 billion tons. As these filaments whip through the galaxy at near light speed, their gravitational pull could distort anything in their path. Now picture a neutron star crossing paths with such a string. The encounter wouldn't be a collision in the traditional sense. The string might slice through the star like a wire through cheese, leaving no visible mark. But the gravitational disturbance could be catastrophic. Here's where the magic happens. As the string passes through the neutron star's core, its ridiculous tension would send shockwaves rippling through the star's quantum fluid. These waves wouldn't just jiggle matter, they'd stir the star's magnetic fields like a blender, twisting them into hypercoiled spirals. Some simulations suggest the string's gravitational shear could amplify the star's magnetic field by a factor of 1,000,000 in milliseconds. It's as if the universe took a perfectly good neutron star and hooked it up to a cosmic car battery, cranking its magnetism to lethal levels. There's a bizarre twist. Cosmic strings might not just amplify fields, they could imprint their own structure onto the star. String theory predicts these defects could carry their own magnetic fluxes, like infinitesimally thin superconducting wires. If a neutron star catches even a tiny segment of this flux during an interaction, it might graft an extraterrestrial magnetic blueprint onto the star's core. The result, a magnetar with a field pattern unlike anything born from conventional physics, a fossil signature of the string's passage written in magnetic hieroglyphics. Of course, proving this is another matter. Cosmic strings have never been observed directly, though astronomers have searched for their telltale gravitational lensing effects or ripples in the cosmic microwave background. Some speculate that fast radio bursts, those enigmatic millisecond blasts of radio waves, could be the snaps of cosmic strings interacting with neutron stars. Others point to certain magnetars with inexplicably tilted magnetic axes, as if something external violently realigned their fields long after birth. The wildest implication: if cosmic strings are real and can create magnetars, they're not just relics, they're active sculptors of the universe, still shaping its most extreme objects 14 billion years after the Big Bang. And that raises an eerie possibility. Somewhere out there, a cosmic string might be drifting toward another unsuspecting neutron star, ready to turn it into the next magnetic monster. Deep inside a neutron star's core, matter doesn't just exist, its shape shifts under pressures so extreme, the rules of physics rewrite themselves. One of the most startling possibilities is that magnetars might owe their terrifying magnetic fields to exotic phase transitions, sudden, violent shifts in the star's quantum architecture that unleash stored energy like a cosmic pressure valve. Picture water freezing into ice, but instead of ice, you get a superconductor 100 trillion times more powerful than anything on Earth, and the transition itself rips spacetime with magnetic fury. The key lies in the neutron star's interior, where protons normally outnumbered by neutrons 100 to 1 can form Cooper pairs, slipping into a frictionless superconducting state. In ordinary neutron stars, this superconductivity stays relatively tame, but in magnetars, something far wilder might occur. As the star cools over centuries, its core could undergo a cascading phase transition, where entire regions flip from normal matter into a superconducting fluid in a matter of seconds. When this happens, magnetic fields trapped in the material get violently expelled, like squeezing toothpaste from a tube. Except the toothpaste is a magnetic field strong enough to power a civilization, and the tube is a 12-mile-wide nuclear inferno. What makes this explosive is something called the Meissner effect, the tendency of superconductors to eject magnetic fields from their interior. On Earth, this causes magnets to levitate harmlessly over chilled superconductors. But in a neutron star, the effect scales up to apocalyptic levels. Simulations suggest that during a core-wide phase transition, the sudden expulsion of magnetic flux could amplify the star's external field 1,000-fold in minutes. It's as if the star had been hiding a second magnetic heart all along, only to reveal it in a single seismic event. There's another layer to this chaos. Neutron star cores might not transition uniformly. Some regions could flip into superconducting states faster than others, creating turbulent boundaries where magnetic fields tangle, snap, and reconnect. These discontinuities might trigger starquakes, magnetar flares so powerful they briefly outshine the Milky Way. The scariest part, we might have already detected the aftermath. Some magnetars show sudden field bumps, unexplained jumps in magnetic strength that align eerily with predictions of phase transitions occurring in their depths. Yet mysteries linger. Why don't all neutron stars undergo these transitions? The answer might involve subtle differences in composition. Stars born with slightly more protons or with quark matter lurking in their cores could be primed for explosive phase changes. Others speculate that external triggers, like accretion from a companion star or dark matter buildup, might destabilize the core's delicate balance. The implications are staggering. If this theory holds, magnetars aren't just born extreme. They evolve into monsters, their cores crystallizing into quantum states we can barely imagine. And every time one of these stars cracks under magnetic strain, it might be sending us a message written in the twisted language of superconductivity. quantum phase changes, and the raw power of a universe forever rewriting its own rules. Neutron stars don't always dine alone. Some feast on their surroundings, and what they consume might transform them into magnetars. When a neutron star orbits a companion star, it can siphon off material, pulling gas into a swirling disk before devouring it. Normally, this process powers bright X-ray emissions, but if that infalling material carries its own intense magnetic fields, something far stranger could happen. The star might not just grow heavier, it could become exponentially more magnetic, absorbing the disk's ferocity like a cosmic sponge. This isn't ordinary accretion. Picture a neutron star surrounded by a disk of superheated plasma, threaded with magnetic fields stronger than anything in our solar system. As material spirals inward, those field lines don't just vanish, they get dragged along, twisted into helical coils by the star's gravity. With every rotation, the disk acts like a conveyor belt, delivering not just matter but magnetism, implanting foreign fields into the star's crust. Over time, this steady diet could amplify the neutron star's own field to magnetar levels, like a blacksmith hammering iron into a permanent magnet. The mechanics are even wilder up close. In highly magnetized disks, turbulence can trap fields in eddies, preventing them from dissipating as they approach the star. Some simulations show these trapped flux tubes punching through the star's surface like needles, stitching external magnetism directly into its superfluid core. Other models suggest the accreted material might form temporary magnetic mountains, lopsided crustal bulges where field lines bunch up, creating localized hotspots of insane magnetic pressure. There's precedent for this. Astronomers have spotted neutron stars where accretion seems to be altering their magnetic fields in real time. Take JRO J1744-288, a system where X-ray pulses suggest the star's field weakens during feeding frenzies only to rebound afterward, as if the digested magnetism reorganizes into something new. Even more telling are transitional millisecond pulsars, which switch between accretion-powered and rotation-powered states, their magnetic personalities shifting with their meals. Yet the theory has hurdles. Why don't all neutron stars with accretion disks become magnetars? The answer might lie in the disk's origin. Material stolen from a magnetically hyperactive companion like a B star with a ferocious stellar wind could deliver stronger fields than gas from a tame sun-like star. The angle of accretion matters too. Direct impacts might bury fields deeper, while glancing inflows could smear them across the surface like magnetic graffiti. The most tantalizing clue comes from magnetar ages. Some of the youngest magnetars, like Swift J1834.9-0846, show evidence of recent accretion, as if their magnetism was handed to them by their last meal. If confirmed, it would mean magnetars aren't always born monsters, sometimes they're made. Most neutron stars spin fast, but some are born spinning so recklessly they blur the line between star and cosmic blender. This theory suggests that for a neutron star to become a magnetar, it needs more than just a violent collapse. It needs a rotational kick so extreme, the star's own spin becomes the engine of its magnetic nightmare. Think of a figure skater pulling their arms in to spin faster, except this skater is a stellar core collapsing from the size of Earth to a city in milliseconds, and the spin reaches speeds that would fling surface material into space if not for gravity's death grip. When a neutron star is born rotating hundreds of times per second, every fluid motion inside it, from the quantum whirlpools in its superfluid core to the seething plasma near its crust, gets whipped into a frenzy. That chaos doesn't just create magnetic fields, it supercharges them like a turbine hooked up to a galactic power grid. The numbers defy logic. A typical neutron star might rotate 30 times per second at birth, already dizzying. But magnetar candidates, some models suggest they could hit 600 rotations per second initially, their equatorial surfaces moving at a third the speed of light. At those speeds, differential rotation between the star's layers becomes catastrophic. The core's superfluid neutrons and protons, already behaving like quantum soup, get stirred into vortices that twist magnetic field lines into braids hotter than the sun and denser than diamond. We've actually spotted potential evidence for this. The Crab pulsar, a neutron star born in a supernova observed in 1054, spins 30 times per second respectively fast, but nowhere near Magnetar territory. Compare that to XTJ 1739-285, a Magnetar whose slow present-day spin hints it must have been born spinning wildly before magnetic braking slammed the brakes. The difference, like comparing a merry-go-round to a jet turbine, but spin alone isn't enough. Timing is everything. To forge a Magnetar, the star needs to sustain that rotational violence long enough for the magnetic amplification to freeze in. Too short and the fields dissipate as the star settles. Too long and the star might tear itself apart. The sweet spot might be mere minutes, a frantic window where the star's interior remains fluid enough for motion to amplify fields, but not so turbulent that it destroys them. There's a dark twist to this theory. Some hyper-rotating neutron stars might not survive infancy. If the spin is too extreme, centrifugal forces can overpower gravity, causing the star to quake violently, not just cracking its crust but potentially fragmenting entirely. These doomed stars might flare brilliantly as magnetars for days or weeks before collapsing into black holes, their magnetic screams cut short. Yet the biggest question remains unanswered. What gives some neutron stars this insane rotational kick in the first place? The answer might lie in the final moments before collapse, stars that rotate unusually fast before death, or those in binary systems where a companion star dumps angular momentum into them, could pass that spin to their corpses. Others might get a last-second torque from asymmetric supernova explosions, like a cosmic hammer striking the core off-center. One thing's clear, in the Magnetar birth lottery, speed kills. And for the stars born spinning fast enough, the prize isn't a peaceful afterlife. It's a magnetic storm with no end in sight. A neutron star's crust isn't just solid. It's a seething, reactive landscape where magnetic field lines twist, tangle, and occasionally snap like overstretched rubber bands. When these lines break, they don't just fade away, they unleash a phenomenon called magnetic reconnection, a violent reordering of the star's magnetic architecture that can concentrate energy so intensely, it transforms ordinary neutron stars into temporary magnetars. Picture a game of tug-of-war where both sides suddenly drop the rope. The energy stored in that tension doesn't vanish, it explodes outward in a chaotic burst. Now replace the rope with magnetic field lines under enough pressure to crack atomic nuclei, and the players with forces powerful enough to warp spacetime. When these fields reconfigure, they don't just release energy, they supercharge it, squeezing magnetic flux into pockets so dense, they rival the fields of magnetars for milliseconds. These aren't just flares, they're magnetic lightning strikes forged in the crust's quantum furnace. The process starts with strain. A neutron star's crust, though only a meter thick, is under unimaginable stress. Gravity compresses it, while magnetic forces push outward. Over time, this tension distorts the crust's lattice of iron nuclei into a patchwork of magnetic domains, some pointing north, others south. Where these domains meet, field lines kink like bent paper clips, storing energy like coiled springs. Eventually, the pressure becomes too much. The lines snap, reconnecting in new configurations. And in that instant, the stored magnetic energy converts into heat, radiation, and particle acceleration. What makes this explosive is scale. A single reconnection event on a neutron star can unleash more energy than a billion volcanic eruptions. But here's the twist: that energy doesn't dissipate evenly. Some simulations show how reconnection can funnel magnetic flux into narrow columns, amplifying local field strength 1,000-fold in microseconds. It's as if the star's crust becomes a hall of mirrors, focusing diffuse magnetism into laser-like beams capable of tearing matter apart. We might have already witnessed this. Magnetar flares, those sudden, galaxy-outshining bursts, often show X-ray signatures consistent with violent reconnection. Some even exhibit double peaks, where an initial burst is followed seconds later by an even brighter flash, exactly what you'd expect if the first reconnection destabilized adjacent fields, triggering a runaway chain reaction. But the most tantalizing clue comes from low-frequency quasi-periodic oscillations detected in some Magnetar flares. These subtle vibration patterns match theoretical predictions for crustal quakes triggered by reconnection, where snapping field lines send seismic ripples through the star like a gong struck by an invisible hammer. Yet mysteries persist. Why do some neutron stars experience crust-shattering reconnection while others don't? The answer might lie in their birth. Stars with slightly uneven crusts, perhaps due to asymmetric supernova or exotic core compositions, could develop more stressed magnetic tangles, priming them for explosive reconnection. Others speculate that external triggers like asteroid impacts or dark matter annihilations might nudge stable systems into chaos. One thing's certain: magnetic reconnection doesn't just explain Magnetar flares, it suggests these stars might flicker between states. Ordinary neutron stars could, for brief moments, become magnetars in patches, their crusts lighting up with magnetic wildfires before settling back into quiet. If true, it means the line between neutron stars and magnetars isn't as fixed as we thought, and that somewhere out there, a dormant star might be one crustal snap away from awakening as a cosmic monster. Deep within a neutron star's core, the rules of ordinary physics dissolve into quantum chaos. But what if that chaos isn't random at all? Quantum vortex alignment proposes that magnetars might owe their apocalyptic magnetic fields to trillions of microscopic whirlpools, spinning in eerie unison like a perfectly choreographed cosmic ballet. These aren't just any vortices, they're fractures in the fabric of reality itself, where the star's superfluid neutrons twist into spirals so precise they amplify magnetism to impossible extremes. The stage for this phenomenon is the star's inner core, a place where matter stops behaving like particles and starts acting like a single, rippling quantum ocean. Here, neutrons pair up into Cooper pairs, the same phenomenon that creates superconductivity on Earth, but scaled up to cosmic insanity. As these pairs flow without friction, they form vortices, each one a microscopic tornado spinning with quantized precision. In most neutron stars, these vortices point in random directions, their magnetic effects cancelling out. But in magnetars, something extraordinary might happen. The vortices align. Imagine a million compass needles suddenly flipping to face the same direction. Now replace those needles with whirlpools of superfluid neutrons, each one dragging magnetic field lines like cosmic fishing nets. As these vortices lock into alignment, their combined pull stretches and concentrates the star's magnetic field into a unified, planet-sized force. Theoretical models suggest this process could amplify a neutron star's magnetism 1,000-fold, not through brute force, but through quantum coordination on a scale we can barely comprehend. The trigger for this alignment might be the star's birth spin. Rapid rotation could act like a cosmic centrifuge, forcing vortices to organize along the spin axis like iron filings in a magnetic field. Alternatively, quantum fluctuations in the star's early moments might nudge a few vortices into alignment, creating a domino effect where neighboring whirlpools snap into lockstep. Some simulations even suggest that vortex alignment isn't static. It could pulse in waves, with synchronized regions suddenly dissolving and reforming, explaining why some magnetars show erratic flares. There's tantalizing evidence hidden in magnetar slowdown rates. As these stars age, their spin decays under magnetic braking, but some decelerate faster than others. Quantum vortex models predict that perfectly aligned vortices would transfer angular momentum more efficiently to the star's crust, matching observations of magnetars with the most extreme braking rates. Even more compelling are glitches, sudden spin jumps where the star's crust briefly outpaces its core. These could be moments when misaligned vortex clusters abruptly snap into harmony, releasing pent-up energy like a coiled spring. Yet mysteries remain. How do vortices maintain alignment in the face of turbulence? Some theorists propose that magnetic tension between vortices acts like invisible threads, keeping them locked in place. Others suggest that exotic particles like hyperons or quark condensates in the core might stabilize the vortex lattice like cosmic glue. And if vortex alignment can be disrupted, say, by a starquake or accretion event, could that turn a magnetar back into an ordinary neutron star? One thing's certain. If this theory holds, magnetars aren't just magnets, they're quantum orchestras, playing symphonies of spin and magnetism on strings we're only beginning to detect. And somewhere in that subatomic harmony, the universe might be hiding the secrets of its most violent magnetic monsters. In the first seconds after a neutron star's violent birth, its interior isn't just hot, it's a maelstrom of plasma churning with the energy of a billion suns. This electromagnetic turbulence theory suggests that within this chaotic whirlpool, magnetic fields don't just grow stronger, they're stretched, twisted, and supercharged through a process that makes a hurricane look like a gentle breeze. Picture the star's core as a cosmic washing machine filled with liquid nuclear matter spinning at relativistic speeds. As different layers of this superheated plasma collide and shear past each other, they create fractal eddies or swirling currents within currents, each one acting like a microscopic dynamo. These turbulent motions don't just carry heat, they grab magnetic field lines like invisible ropes, whipping them into tighter and tighter coils through a phenomenon called turbulent dynamo amplification. Where ordinary dynamos might multiply field strength by thousands, turbulence in these extreme conditions could crank it up by factors of a quintillion. What makes this process explosive is its randomness. Unlike orderly dynamo theories where fields grow predictably, turbulence introduces chaotic elements, magnetic knots that form and dissolve in milliseconds, current sheets thinner than atoms where fields violently reconnect, and whirlpool-like structures called plasmoids that trap and concentrate magnetism like cosmic pressure cookers. Some simulations show field lines becoming so tangled they resemble a ball of quantum spaghetti, with energy densities surpassing anything achievable in Earth's most powerful particle accelerators. The key to this runaway amplification lies in something called the magnetic Reynolds number, a measure of how easily magnetic fields can diffuse through a plasma versus how much they get stretched and folded by turbulence. In newborn neutron stars, this number reaches astronomical values, meaning fields get twisted faster than they can dissipate. It's like stirring honey into a vortex, except the honey is a superfluid quark gluon plasma, and the spoon is space-time itself being warped by the star's rotation. We might actually have observational evidence for this chaos. Some young neutron stars exhibit wildly fluctuating X-ray emissions in their first hours, exactly what you'd expect if their surfaces were being bombarded by magnetic turbulence bubbling up from the depths. Even more telling are the polarization patterns in magnetar flares, which show intricate spirals and loops suggesting fields weren't just amplified, but intricately braided by violent fluid motions. Yet mysteries remain. Why does turbulence create magnetars in some stars but not others? The answer might lie in the initial seed field's tiny magnetic imperfections in the collapsing progenitor star that turbulence can exploit. Like how a single grain of sand can trigger an avalanche, these microscopic variations could determine whether turbulence builds a structured magnetic monster or just dissipates into harmless eddies. Others speculate that turbulence needs time to work. Stars born spinning too fast might tear apart before the process completes, while those spinning too slow might not generate enough shear to sustain the chaos. The most fascinating implication: this turbulence might not stop at birth. Some models suggest magnetars could maintain internal weather patterns for years, hidden storms where plasma cyclones continually regenerate magnetic energy, explaining why these stars keep flaring long after their formation. If true, it means a magnetar isn't just a magnetic fossil, it's a living, churning entity, its heart still beating with the echoes of its catastrophic birth. Most of space seems empty until you realize it's threaded with invisible magnetic fields like a cosmic spiderweb. Theory 18 takes us outside the star itself, proposing that magnetars might owe their ferocious magnetism not to how they're born but where. Imagine a neutron star forming in a region of the galaxy where the interstellar medium, the thin gas between stars, is already magnetized to extremes. Like a seed planted in pre-fertilized soil, the star wouldn't need to generate its own insane magnetic fields from scratch. Instead, it could inherit them from its environment, sucking up these primordial magnetic energies like a cosmic sponge during its violent birth. This isn't as far-fetched as it sounds. We've known for decades that the interstellar medium isn't uniform. Some regions, like the twisted filaments near supernova remnants or the turbulent wakes of colliding gas clouds, show magnetic fields thousands of times stronger than average. These pockets act like celestial electromagnets with field lines so dense they can influence how stars form. When a massive star collapses in one of these zones, its core wouldn't just collapse into a neutron star, it'd be collapsing into a pre-magnetized cocoon, dragging those external field lines inward and compressing them to absurd densities. Think of it like this: take a weak bar magnet and squeeze it into a sphere the size of a marble. The field inside doesn't disappear, it concentrates, multiplying in strength as the volume shrinks. Now replace the magnet with a light-year-wide cloud of magnetized plasma and the marble with a neutron star. The math is staggering. Even modest interstellar fields, when crushed to neutron star densities, could theoretically reach magnetar levels. Some simulations suggest that a progenitor star forming in a region with just 10 times the galactic average magnetic field could birth a neutron star with a field amplified a billionfold. But how do these magnetic pockets form in the first place? One culprit might be dead stars. When massive stars die in supernova, they don't just explode. They inject magnetized turbulence into their surroundings, creating twisted magnetic knots that linger for millennia. Another possibility involves galactic collisions, where entire gas clouds smash together, stretching and amplifying their embedded fields like cosmic taffy. There's even evidence that certain regions near the Milky Way's core, where magnetic forces warp entire star-forming regions, might act as natural magnetar factories, churning out pre-magnetized stellar nurseries. The smoking gun could lie in magnetar distribution. If this theory holds, magnetars should cluster in parts of the galaxy with unusually strong interstellar magnetism. Intriguingly, several known magnetars, like SGR 1806-20, sit near supernova remnants or active star-forming regions, precisely where you'd expect these magnetic enhancements. Even more telling are the wandering magnetars, ones that seem to have rocketed away from their birthplaces at insane speeds. If they formed in highly magnetized environments, their natal kicks could have launched them like cosmic slingshots, trailing magnetic fingerprints from their origins. Yet challenges remain. Not all magnetars live in obviously magnetic neighborhoods, and some regions with extreme interstellar fields don't seem to produce them. This suggests that while the pre-magnetized medium might give neutron stars a magnetic head start, other factors, like rotation or core composition, could determine whether they cross the threshold into true magnetar territory. There's also the puzzle of timescales. Interstellar fields fluctuate over millions of years, while magnetars are relatively short-lived. Did these stars just get lucky, forming during a temporary magnetic peak in their local environment? What's fascinating is the implication. If magnetars can be forged by their surroundings, it means the universe isn't just creating magnetic monsters randomly. It's sculpting them deliberately in hidden workshops where the very fabric of space comes pre-wired for extremity. And that raises a tantalizing thought somewhere out there. An unsuspecting gas cloud might already hold the seeds of the next great cosmic magnetic beast. Neutron stars don't always age gracefully. Sometimes they shudder violently in what astronomers call a glitch, a sudden hiccup in their rotation that betrays turmoil beneath the surface. These events aren't just curiosities. They might be the key to understanding how some neutron stars transform into magnetars. Picture a star's crust, a crystalline shell a kilometer thick but so dense it's harder than diamond. Over time, this crust strains under the competing forces of gravity and magnetism until snap, it fractures like an overstressed bridge. But here's the twist: when the crust breaks, it doesn't just jostle the star's spin, it rewires its magnetic heart. The process starts with stress buildup. As a neutron star cools, its superfluid core slows faster than the rigid crust, creating a rotational mismatch that stretches the magnetic fields threading through both. Like twisting a rubber band until it's ready to snap, this sheer energy accumulates for years until the crust can't take it anymore. In an ordinary glitch, the crust simply catches up to the core in a sudden jump. But in a magnetar-forming glitch, something wilder happens. The crust fractures asymmetrically, splintering into plates that slide like tectonic faults. These shifts don't just redistribute spin, they drag the star's magnetic field lines with them, knotting them into concentrated bundles where the crust buckles. Simulations reveal how explosive this reorganization can be. When crustal plates shear past each other, they create magnetic scars, localized zones where field lines pile up like traffic in a cosmic bottleneck. Some models show these scars amplifying surface magnetic fields by a factor of 100 in milliseconds, turning patches of the star into temporary magnetar-like zones. Over repeated glitches, these hotspots could merge, transforming the entire star into a magnetar through a cascade of crustal adjustments. There's observational fire to match this theoretical smoke. The Magnetar SGR 1900+14 exhibited a colossal glitch in 1998, where its spin jumped abruptly just before a massive flare, as if the star's crust had finally ripped open, unleashing pent-up magnetic energy. Even more telling are anti-glitches, rare events where the star slows down instead of speeding up. These might represent moments when the crust's movement tangles magnetic fields so severely they act like cosmic brakes, sapping rotational energy to power magnetic amplification. What's chilling is the scale of these fractures. A neutron star crust under stress doesn't crack gently, it fails catastrophically, with quakes registering up to magnitude 32 on the Richter scale. The energy released could liquefy portions of the crust, allowing magnetic fields to reconfigure freely before refreezing into new, more complex arrangements. Some researchers speculate that particularly violent starquakes might even expose the star's superconducting core, letting internal magnetic flux erupt to the surface like lava from a volcano. Yet mysteries persist. Why do some glitches lead to magnetic amplification while others don't? The answer might lie in the star's magnetic geometry, how deeply its original field lines are anchored in the core. Stars with shallow fields might see them reshuffled like a deck of cards during a quake, while those with deep roots could resist reorganization. There's also the wild card of superconducting vortices in the core. If these quantum whirlpools get jostled during a glitch, they might funnel additional magnetic energy outward like lightning rods. The implications are staggering. If glitches can forge magnetars, it means these magnetic monsters aren't just born. They can evolve over time, their fury building through a series of cosmic growing pains. And that raises an eerie possibility. Somewhere out there, an otherwise ordinary neutron star might be one crustal snap away from awakening as the next great magnetic terror of the galaxy. Neutron stars and black holes, the universe's most extreme neighbors, might be engaged in a cosmic tug of war so violent it could forge magnetars through sheer gravitational sabotage. Theory 20 throws us into this gravitational maelstrom, where a neutron star orbiting too close to a black hole doesn't just risk annihilation. It could emerge from the ordeal magnetically supercharged, its fields twisted and amplified by forces that warp the fabric of spacetime itself. Picture a neutron star skirting the edge of a black hole's event horizon, so close that tidal forces stretch it like taffy. These aren't gentle pulls, their spacetime rips strong enough to distort the star's very structure, kneading its interior like cosmic dough. As the star's crust and core warp under these extreme stresses, the magnetic field lines threading through them don't just bend, they snap and reconnect in chaotic bursts, a process that could supercharge localized magnetic hotspots to magnetar levels. Simulations suggest this tidal massage might not just amplify fields passively, it could actively generate them, like rubbing a balloon to build static. Except the balloon is a 12-mile-wide nuclear inferno, and the rubbing is done by a black hole's gravitational fists. But tides aren't the only danger or opportunity. If the neutron star orbits within the black hole's accretion disk, it could plunge through rivers of superheated plasma, dragging embedded magnetic fields along like a ship collecting seaweed. Every pass through this magnetized soup might implant fresh flux into the star's crust, steadily ratcheting up its magnetic energy over millennia. Some models even suggest that plasma avalanches torn from the disk could crash onto the neutron star's surface, delivering concentrated magnetic injections with each impact. The most extreme scenario involves the black hole itself as an unwitting accomplice. If the neutron star's orbit decays, spiraling ever closer, the black hole's spin could act like a cosmic dynamo, transferring rotational energy directly into the star's magnetic field through a process called frame dragging. Imagine a spoon stirring honey, except the spoon is a black hole's rotation twisting spacetime itself, and the honey is the neutron star's quantum fluid. This relativistic battering might not just amplify the star's magnetism, it could reorient it entirely, cranking the field into alignment with the black hole's spin axis like a compass needle jerked toward a magnet. Evidence for this violent partnership is scarce but tantalizing. A handful of ultra-luminous X-ray sources mysterious objects pumping out more energy than physics easily explains. Could be neutron stars flirting with black holes, their emissions boosted by magnetic torture. Even more provocative are the fast radio bursts that seem to originate near supermassive black holes. Some theorists suggest these could be magnetars screaming under gravitational stress, their crusts cracking under tides while their magnetic fields short-circuit into bursts of radio energy. Yet the biggest question remains, could such a neutron star survive long enough to become a magnetar, or would the black hole shred it first? The answer might depend on the black hole's size. Stellar mass black holes could rip a neutron star apart within orbits, but supermassive ones might offer a gentler, if that word even applies, environment where tides amplify fields without immediate destruction. Either way, the universe seems to have a cruel sense of irony. The same forces that could create a magnetar might also be the ones that ultimately doom it. This theory forces us to confront a thrilling possibility that magnetars might not just be born in isolation, but forged in the most violent relationships the cosmos has to offer. And if true, it means the universe doesn't just build magnetic monsters, it pits them against gravitational titans, watching to see which force will break first. When a star explodes as a supernova, the show isn't over when the fireworks fade. Sometimes the universe encores with a deadly second act. As the outer layers blast outward at millions of miles per hour, a fraction of that material, weighed down by gravity, reverses course in a phenomenon called fallback. This isn't just debris raining back down. It's a magnetic hailstorm where chunks of star stuff, still crackling with their progenitors' ferocious magnetic fields, slam into the newborn neutron star like cosmic shrapnel. The physics behind this is brutally elegant. During the explosion, the star's outer layers don't just vanish, they're temporarily suspended in a teetering balance between escape velocity and gravitational pull. For most supernova, the energy wins, flinging material into space forever. But in certain cases, especially with massive, messy explosions, some of that gas stalls, lingers, then plummets back toward the collapsed core. As it falls, it doesn't come empty-handed. Stellar material is threaded with magnetic fields forged in the star's death throes, and when it crashes onto the neutron star's surface, those fields don't just dissipate, they embed themselves like tattoos in the star's crust. Here's where the nightmare fuel ignites. Fallback isn't a gentle drizzle, it's a hyperviolent downpour. Simulations show these returning fragments striking the neutron star at half the speed of light, their kinetic energy converting into heat and magnetic turbulence on impact. The star's crust, already a lattice of atomic nuclei under unimaginable strain, fractures under the barrage, allowing the incoming magnetic flux to penetrate deeper than surface level. Some models suggest this process could inject fresh magnetic energy directly into the star's superconducting core, turning it into a reactor where fallback acts like somebody pouring gasoline on a smoldering fire. We might have already spotted the aftermath. The Magnetar Swift J1834.9-0846, discovered in 2011, sits shrouded in a thick cloud of debris, exactly what you'd expect if it recently gorged on fallback material. Even more telling is its magnetic field strength, nearly 1,000 trillion Gauss, far beyond typical neutron stars. Then there's the case of the Christmas burst from SGR 1627-41 in 2004. This Magnetar's violent flare coincided with a sudden infrared brightening, as if it had just swallowed a chunk of magnetized star stuff, triggering a magnetic indigestion powerful enough to be seen across the galaxy. But fallback isn't just about quantity, it's about timing. The most dramatic magnetic amplification might happen in the star's first days, when its crust is still hot enough to be malleable. As fallback material smashes into this plastic surface, it doesn't just transfer magnetic energy, it sculpts the field lines, twisting them into braids and knots that resist decay. Picture a blacksmith hammering red-hot iron, except the hammer is a mountain of plasma, and the anvil is a neutron star's surface frozen mid-quake, the wildest implication. This process might not be one and done. Some magnetars show periodic flares spaced years apart, behavior hard to explain with internal processes alone. Could these be signs of delayed fallback, where orbiting debris circles for decades before finally spiraling in, delivering fresh magnetic boosters long after the star's birth? If so, magnetars might not just be born extreme, they could be repeatedly recharged by the ghostly remains of their own destruction. Yet the biggest question remains unanswered. Why do some supernova produce such dramatic fallback while others don't? The answer might lie in the progenitor star's rotation. Fast-spinning stars could sling their outer layers into chaotic orbits, ensuring some material lingers in a deadly halo before falling back. Others speculate that asymmetric explosions where the supernova detonates lopsidedly might leave pockets of gravitationally bound debris ripe for later collapse. What's clear is this: if fallback really can forge magnetars, it means a star's death isn't always a clean break. Sometimes the corpse gets haunted by the very ashes it tried to scatter, and from that haunting, something far stranger rises. At the quantum level, neutron stars might be hiding a secret ingredient, one that could turn them into magnetars by default. The strange star hypothesis takes us beyond neutrons into a realm where matter itself dissolves into its most fundamental parts. Picture a star's core under such extreme pressure that neutrons, normally stable particles, shatter like glass, breaking apart into a seething ocean of free-floating quarks. But these aren't just any quarks. Under these insane conditions, some might transform into strange quarks, an exotic variant rarely seen outside particle accelerators. This transition could unlock magnetic properties so extreme They make ordinary neutron stars look tame by comparison. The magic lies in how quarks behave when freed from their neutron prisons. In normal matter, quarks are forever bound in groups of three, forming protons and neutrons. But in a strange star's core, they're unleashed, swimming freely in a quantum soup where up, down, and strange quarks mingle. This isn't just a particle zoo, it's a superconducting powerhouse. Strange quarks have a unique property. They can form Cooper pairs, just like electrons in a superconductor, but with a critical difference. These pairs don't just conduct electricity without resistance, they can trap and amplify magnetic fields to levels that defy conventional physics. Here's where things get surreal. In a conventional neutron star, magnetic fields are limited by how much energy the star's rotation or turbulence can inject. But in a strange star, the quark soup's superconductivity changes the rules entirely. Magnetic flux gets frozen into the star's core like bugs in amber, with field lines unable to decay or dissipate. Over time, these trapped fields could organize into microscopic vortices, each one a tornado of magnetic energy narrower than an atom but powerful enough to distort spacetime. The combined effect, a star where the entire interior acts like a perfect magnetic resonator, amplifying even modest seed fields into Magnetar strength monsters. There's observational spice to back this up. Some Magnetars emit X-ray pulses with energy signatures that don't quite match predictions for pure neutron matter. Instead, they align eerily with models of quark surfaces emitting magnetic bursts as their crusts crack under stress. Even more compelling are the temperature discrepancies. Certain magnetars cool faster than neutron star models predict, as if something inside them conducts heat far more efficiently. That something could be quark matter, whose superconducting properties would let energy radiate away like heat, vanishing into a cosmic heat sink. Yet the strangest twist isn't in the stars, it's in the sky around them. If strange stars exist, they might produce telltale quark nova explosions when their crusts collapse into their quark cores. These eruptions would spray strange matter into space, potentially creating heavy elements we've never seen in nature. Intriguingly, some supernova remnants near known magnetars contain anomalous metal abundances that resist easy explanation, chemical fingerprints hinting at a formative catastrophe stranger than a typical stellar death. Of course, the theory has skeptics. No experiment has ever definitively produced stable strange matter, and some physicists argue quark stars would be too unstable to exist. But if they're real, if even a fraction of magnetars are actually strange stars in disguise, it would mean the universe harbors objects even more radical than we've dared imagine. Not just dead stars, but quantum alchemy labs where the rules of matter itself are rewritten, and magnetism becomes not a byproduct but the very language of their existence. As a massive star collapses into a supernova, its magnetic field doesn't just vanish, it gets trapped and crushed like a cosmic butterfly in amber. This is the essence of magnetic flux freezing, a process where the star's magnetism locks into its plasma during collapse, preserving its fields in a gravitational vice grip. The physics hinges on conductivity. In the star's outer layers, ionized gas behaves like a near-perfect conductor, preventing magnetic field lines from slipping away as gravity compresses everything to neutron star densities. It's not just preservation, it's compression on a scale that defies intuition, where field lines that once gently wrapped around a star millions of miles wide get squeezed into a sphere smaller than a city. Think of it like pressing on a balloon covered in ink. As you shrink the balloon, the ink lines don't fade, they grow darker, tighter, more concentrated. Now replace the balloon with a dying star, the ink with magnetic flux, and your hand with the irresistible crush of gravity. The math is staggering. If a progenitor star had a modest magnetic field of just 1000 Gauss, similar to a sunspot, flux freezing during collapse could amplify it to a quadrillion Gauss in the resulting neutron star. That's not just amplification, it's transformation, turning what was once a stellar magnetic whisper into a cosmological scream. But the process isn't uniform. As the star implodes, turbulence in the collapsing layers can twist frozen flux into braids and knots, creating localized magnetic hotspots far stronger than the background field. Some simulations show these tangles forming magnetic towers, column-like structures where field lines are so tightly wound. They act like cosmic particle accelerators, funneling energy toward the star's poles. This could explain why some magnetars exhibit asymmetrical fields, with one hemisphere significantly more magnetic than the other. These distortions might even seed future starquakes as pent-up magnetic tension strains the neutron star's crust to the breaking point. There's tantalizing evidence hidden in supernova remnants. When astronomers mapped the Crab Nebula's magnetic field, they found intricate swirls aligning eerily with predictions of flux freezing during its progenitor star's collapse. Even more compelling are the filamentary arcs in Cassiopeia, threads of plasma that appear to trace the paths of frozen magnetic fields from the explosion. If these patterns reflect the original star's magnetism, they'd imply flux freezing doesn't just preserve fields, it sculpts them, imprinting the chaos of collapse into the nebula's very structure. Yet mysteries linger. Why do some supernova produce magnetars via flux freezing while others create neutron stars with ordinary fields? The answer may lie in the progenitor's rotation. Rapidly spinning stars could stretch and shear their magnetic fields during collapse, like taffy in a cosmic puller, enhancing the freezing effect. Others speculate that pre-collapse convection, the churning of plasma in the star's final days, might tangle the magnetic geometry, setting the stage for extreme amplification when freeze-in occurs. The most profound implication: flux freezing suggests magnetars might carry literal pieces of their ancestors' souls, not as matter, but as magnetism. Those apocalyptic fields we detect today could be direct descendants of the gentle loops that once cradled a living star's surface, now reborn in a form their creators could never have imagined. It's a ghost story written in magnetic ink, where the past never truly dies, it just gets compressed, twisted, and unleashed anew. When a massive star collapses into a supernova, the explosion doesn't just blast matter into space. It floods the universe with trillions upon trillions of ghostly particles called neutrinos. For a split second, these invisible messengers carry away more energy than the sun will produce in its entire lifetime. But what if this neutrino tsunami doesn't just vanish into the cosmos? What if, in certain supernova, these particles escape unevenly, and their lopsided flight could twist space itself into a magnetic monster? This is the heart of neutrino-driven amplification, a theory where asymmetry in the dying star's neutrino emission becomes the sculptor of magnetar strength fields. Picture the star's core in its final milliseconds, a seething orb of neutrons and protons being crushed by gravity, so dense that even neutrinos, which normally pass through planets like ghosts, get momentarily trapped. As these particles ricochet in the chaos, they don't just escape randomly. Turbulence in the collapsing star, or perhaps a slight distortion in its shape, can funnel more neutrinos out one side than the other. This imbalance doesn't just carry away energy, it carries away momentum, like rockets firing unevenly from a spaceship. The result: the newborn neutron star gets a vicious gravitational kick in one direction, while the neutrinos recoil, torques the star's interior like a wrench twisting a bolt. Here's where magnetism enters the fray. That neutrino-induced spin isn't just rotation, it's a swirling current of charged particles, a dynamo fueled by the most energetic particles in the universe. As the star's core gets yanked into this spiraling motion, electrons and protons still swimming in the neutron soup get whipped into frenzied orbits. Each charged particle becomes a microscopic current, and where there's current, magnetic fields follow. Supercomputer simulations reveal how extreme this effect can be. neutrinos escaping just 10% faster from one pole could amplify the star's magnetic field by factors of 1,000 within seconds. But the real magic happens deeper. Neutrinos don't just nudge matter, they change its very behavior. In the star's quark-gluon plasma core, neutrino interactions might temporarily freeze quantum vortices, structures normally flitting about randomly. Like traffic cops at a quantum intersection, these pinned vortices could force spinning particles into organized streams, channeling their motion into coordinated magnetic currents. Some models suggest this neutrino shepherding could create magnetic flux ropes, thick bundles of field lines coiled like dynamo, that punch through the star's crust with enough force to rival a Magnetar's surface field. We might have witnessed the aftermath of this process. The supernova remnant Cassiopeia shows a bizarre jet of material blasted out at nearly light speed, exactly the kind of structure predicted by asymmetric neutrino emission. Even more telling are recent observations of supernova 2020 IK, which exhibited polarized light, a fingerprint of strong, organized magnetic fields sculpted in the explosion's immediate aftermath. Both could be cosmic autographs left by neutrino-driven dynamos in their most violent moments, yet the theory isn't without paradoxes. Why don't all supernova with neutrino asymmetries produce magnetars? The answer may lie in timing. If the star's magnetic field hasn't fully frozen in before the neutrino torque fades, the amplified fields might dissipate like smoke in the wind. Others argue that progenitor stars with pre-existing magnetic twists might be primed to exploit neutrino kicks more efficiently, like a sailboat angled to catch the wind. What's certain is this: if neutrinos really can forge magnetars, it means these elusive particles, so light they were once thought massless, have the power to move mountains. Not earthly mountains, but celestial ones, twisting the carcasses of dead stars into magnetic titans that outshine galaxies. And somewhere in that invisible dance of particles and momentum, the universe might be hiding the blueprints for its most fearsome creations. Deep inside a neutron star's crust, electrons don't just flow, they revolt against the very forces trying to control them. This is the Hall effect writ large on a cosmic scale, where the collective motion of charged particles doesn't just carry current, it rewrites the rules of magnetism. Imagine a river where the water doesn't follow the riverbed but carves new channels midstream, defying gravity itself. Now replace the river with a seething ocean of electrons, the riverbed with magnetic field lines strong enough to distort atoms, and gravity with forces that bend spacetime. That's the Hall effect in a neutron star's crust, a phenomenon so powerful, it could twist ordinary magnetic fields into Magnetar strength monstrosities. The physics at play here is both subtle and catastrophic. In ordinary materials, the Hall effect causes moving electrons to veer sideways when exposed to a magnetic field, creating a voltage perpendicular to their motion. But inside a neutron star's crust, where densities reach 1,000,000 tons per cubic centimeter and magnetic fields are 1,000,000,000,000 times stronger than Earth's, this effect transforms into something far more extreme. Electrons don't just drift slightly off course, they bulldoze through magnetic field lines like cosmic plows, dragging and twisting them into helical coils that amplify their strength exponentially. Some simulations show that over centuries, this relentless electron motion could reorganize a neutron star's entire magnetic architecture, concentrating diffuse fields into localized ropes of magnetic fury. What makes this process explosive is its feedback loop. As electrons reconfigure the fields, those new field geometries alter how electrons move, which further twists the fields. A self-reinforcing cycle where small initial asymmetries snowball into magnetic maelstroms. Picture a snowball rolling downhill, except instead of snow, it's gathering magnetic energy, and the hill is the slope of spacetime itself. The numbers are staggering. Crustal currents could amplify surface magnetic fields by factors of 1,000 in just 10,000 years, a blink of an eye in cosmic terms. There's a brutal elegance to how this unfolds. The neutron star's crust isn't a uniform slab. It's a crystalline lattice of iron nuclei drowning in a sea of free electrons. When magnetic fields penetrate this layer, they don't just sit passively, they become dynamic, living structures. Regions where electron flow is turbulent develop Hall cascades, where magnetic energy transfers from large-scale fields to smaller, knottier configurations. It's as if the crust becomes a magnetic fractal factory, churning out ever more complex patterns until the fields reach breaking point. We might have spotted the aftermath of this process. The Magnetar SGR 0526-66 exhibited a rapid magnetic field evolution over 2 decades, far too fast to explain with conventional models. Its field strength and orientation shifted in ways that align eerily with Hall effect simulations, as if something beneath the surface was relentlessly rearranging its magnetic bones. Even more telling are the Hall drift waves predicted by theorists, subtle oscillations in Magnetar emission that could betray the slow, seismic migration of magnetic domains through the crust. Yet the Hall effect isn't just about creation, it's about destruction. In some scenarios, the same process that amplifies fields can also destabilize them. When electron flows become too chaotic, they can trigger Hall earthquakes, where magnetic stresses rupture the crust in ways that make ordinary starquakes look like hiccups. These events might explain why some magnetars flare unpredictably. Their crusts aren't just cracking under pressure, they're being shredded by their own electromagnetic turbulence. The wildest implication, this process might not be unique to magnetars. Ordinary neutron stars could, over eons, Hall drift their way into magnetarhood, their fields growing stronger and more tangled until they cross the threshold into extreme magnetism. It's a cosmic ticking clock, one where the timer is set by electrons too relentless to ignore, and the alarm is a magnetic scream loud enough to echo across galaxies. Pulsars are cosmic lighthouses spinning neutron stars that sweep beams of radiation across space with metronomic precision. But what if some of these stellar timekeepers harbor a dark secret? Theory 26 flips the script, suggesting that certain magnetars might actually be pulsars that never grew up, stellar remnants whose magnetic fields stubbornly refuse to fade, locking them in a permanent state of magnetic adolescence. The conventional story goes like this. When a neutron star is born, its magnetic field starts strong but gradually weakens over millennia as currents in its crust dissipate. Pulsars, with their weaker but stable fields, represent the mature phase of this evolution. Magnetars, by contrast, were thought to be born different, genetically predisposed to extreme magnetism from their violent origins. But this theory throws that assumption out the window. Instead, it posits that some neutron stars destined to become ordinary pulsars simply stopped aging. Their magnetic fields, through some cosmic quirk, got stuck in their youth, preserving their juvenile ferocity indefinitely. How could this happen? Picture a neutron star's crust shortly after birth, a crystalline lattice seething with electrons trapped between layers of iron nuclei. Normally, these electrons slowly leak away, draining energy from the magnetic fields they sustain. But in certain stars, the crust might crystallize in a way that traps electrons like flies in amber. Imperfections in the lattice, perhaps caused by asymmetric cooling or exotic quantum states, could create microscopic bottlenecks where electron flow grinds to a halt. Without this current decay, the star's magnetic field remains frozen in time, a relic of its explosive birth. There's observational weight to this idea. Some magnetars, like XTJ1810-197, exhibit puzzlingly slow spin rates, far slower than typical young neutron stars, as if they've been braking against an invisible force for millennia. Their magnetic fields also appear oddly clean, lacking the tangled complexity seen in other magnetars. These traits align eerily with predictions for neutron stars whose fields didn't dissipate but instead locked into a stable, high-strength configuration early on. Even more telling are the Magnetar/pulsar hybrids, objects like PSR J1846-0258, which shows bursts of Magnetar-like activity despite having a relatively modest magnetic field. These oddballs might represent transitional cases where a star's field decay stalled partway, leaving it stranded between identities. The implications are profound. If some magnetars are just pulsars that refuse to fade, it means the line between these classes isn't as firm as we thought. The universe, it seems, has a habit of preserving its outliers, not through extraordinary birth, but through the sheer stubbornness of physics itself. And that raises a chilling question. How many other failed pulsars are lurking out there, their frozen fields waiting to snap? Most neutron stars are born alone, but some have cosmic neighbors capable of turning them into magnetars through sheer magnetic bullying. Theory 27 explores this stellar peer pressure where a neutron star orbiting too close to a magnetically hyperactive companion doesn't just share space. It gets its entire magnetic identity rewritten by forces powerful enough to warp the fabric of reality itself. Picture a neutron star caught in the gravitational embrace of a massive, fast-spinning star with a magnetic field thousands of times stronger than our Sun's. As the neutron star orbits, it doesn't just sail through empty space, it plows through a hurricane of magnetized plasma, a stellar wind so charged it could strip planets of their atmospheres. These aren't gentle breezes, they're electromagnetic tsunamis that slam into the neutron star's crust, compressing its native magnetic field like a trash compactor crushing soda cans. Every pass through this charged maelstrom stacks magnetic pressure onto the star, ratcheting up its internal field strength with each orbit. The physics here is brutal yet elegant. As the external field presses inward, it doesn't just squeeze the neutron star's surface, it induces currents deep in its conductive core. These currents generate opposing magnetic fields, which then interact with the external field in a feedback loop that can amplify the star's overall magnetism exponentially. Imagine two mirrors facing each other, reflecting light back and forth until the space between them glows blindingly bright, except instead of light, it's magnetic energy, and the mirrors are the neutron star and its ferocious companion. Over time, this magnetic mirroring effect could transform an ordinary neutron star into a magnetar through sheer environmental stress. There's observational spice to back this up. The binary system HD 54879 contains a massive star with a magnetic field so strong it's visible in optical light orbited by an unseen compact object. While the companion hasn't been confirmed as a neutron star, its X-ray emissions suggest intense magnetic activity. Even more compelling are the magnetic massive stars found in young clusters, blue giants with surface fields strong enough to light up entire nebulae. If these stars eventually collapse into neutron stars while retaining their binary partners, the stage would be set for exactly this kind of external compression scenario. But the most extreme cases might involve not just compression but magnetic grafting. Some models suggest that in tight binaries, the neutron star could actually steal flux tubes from its companion's magnetosphere, splicing these foreign magnetic strands into its own crust like a cosmic organ transplant. These grafted fields wouldn't just add strength, they'd introduce new geometries, potentially creating the twisted, multipolar magnetic configurations seen in some magnetar flares. Yet the process isn't without limits. Too much external pressure could shred the neutron star's crust entirely, triggering apocalyptic starquakes as the magnetic vise tightens. Others speculate that the companion's field might eventually push the neutron star away, like two magnets repelling at close range, explaining why so few magnetars are found in tight binaries today. One thing's certain, if external compression really can forge magnetars, it means these magnetic monsters aren't always self-made. Sometimes they're sculpted by the universe's most demanding roommate stellar partners who don't just share a cosmic apartment, but forcibly remodel it into a magnetic fortress. The vacuum of space isn't as empty as it seems, especially near a neutron star. Quantum physics tells us that even in a void, particles flicker in and out of existence, their fleeting presence governed by the uncertainty principle. But around a neutron star's crushing gravity and titanic magnetic fields, this quantum foam doesn't just flicker, it twists. Theory 28 ventures into this subatomic chaos, asking whether these vacuum fluctuations could become cosmic conspirators, amplifying a neutron star's magnetism to Magnetar extremes through a phenomenon called vacuum polarization. Here's how this quantum sorcery might work. In ordinary space, virtual particle pairs electrons and positrons constantly pop into existence before annihilating too quickly to measure. But near a neutron star, where magnetic fields approach a quadrillion Gauss, these ghostly particles can't just wink in and out unnoticed. The field's sheer strength polarizes the vacuum itself, stretching virtual particles into elongated loops aligned with the magnetic field lines. It's as if empty space becomes a hall of mirrors, reflecting and reinforcing the star's magnetism at the quantum level. Some calculations suggest this effect could locally amplify fields by up to 10%, which sounds modest until you realize that 10% of a neutron star's baseline magnetism is enough to power a small galaxy. The real magic happens in the star's immediate vicinity. As vacuum polarization concentrates field lines, it effectively shrinks the distance between them, increasing their energy density. Imagine 100 rubber bands laid side by side. Now imagine squeezing those same bands into the space of one. The tension skyrockets. In a neutron star's magnetosphere, this quantum crowding could create magnetic hotspots where vacuum effects push field strengths beyond what classical physics should allow. These regions might act like cosmic amplifiers, their quantum-tuned resonance chambers trapping and enhancing magnetic energy until the star's entire exterior crackles with excess. But there's a twist. Vacuum polarization isn't just about amplification, it can also distort. Certain quantum electrodynamics models predict that in ultra-strong fields, vacuum polarization becomes nonlinear, warping field geometries into fractal-like patterns. Instead of neat dipole fields, the star might develop magnetic walls, tiny, hyper-intense vortices where vacuum effects twist field lines into microscopic knots. These knots could store absurd amounts of energy, releasing it in nanoflares when quantum tunneling allows them to snap. Observational hints of this exist. Some Magnetar X-ray bursts show substructure too fine to explain with classical magnetic reconnection alone, as if something far stranger, something quantum, were at play. The wildest implication, this process might not be static. As the neutron star spins, its vacuum-polarized magnetosphere could generate secondary quantum currents, creating a feedback loop where real particles get accelerated, produce gamma rays, and those gamma rays spawn more virtual pairs. The result, a self-sustaining quantum engine where the vacuum itself becomes a participant, pumping the star's magnetic field like a cosmic bellows. It's a far cry from the dead, inert stars of classical astrophysics. This is a neutron star alive with quantum fury, its magnetism eternally refreshed by the seething nothingness around it. Yet mysteries loom. Why don't all neutron stars exhibit these vacuum-boosted fields? The answer might lie in a critical threshold, a magnetic activation energy the star must surpass before vacuum effects become significant. Stars born just below this line might never trigger the feedback cycle, while those nudged over it by other mechanisms like differential rotation or accretion could quantum leap into Magnetar territory. Others speculate that vacuum polarization's impact depends on the star's age. Young, hot neutron stars might excite the quantum vacuum more efficiently than their cooler, older cousins. If this theory holds, it means magnetars aren't just magnets, they're quantum experiments on a cosmic scale. Their surfaces could be the closest things in nature to laboratory setups probing quantum gravity. Their flares the signatures of spacetime itself buckling under magnetic stress. And that raises an electrifying possibility. Some of the universe's most violent phenomena might ultimately trace back to the gentlest of things, the whisper of particles that don't even exist. At the razor's edge between neutron star and black hole lies a cosmic anomaly, the supermassive neutron star. These are stellar corpses so heavy they flirt incessantly with oblivion, hovering just shy of the mass required to collapse into a black hole. Their existence is precarious, balanced on a knife's edge of gravity and quantum pressure, but it's this very instability that might transform them into the universe's most powerful magnetars. What makes these stars different starts with their birth. When a massive star explodes, the collapsing core must shed enough mass to avoid immediate black hole formation. But sometimes it barely makes the cut, retaining just enough material to stabilize as a neutron star, yet teetering on the brink. This near-critical mass triggers extreme conditions even by neutron star standards. The core doesn't just compress, it hypercompresses, squeezing matter into states so dense, protons and electrons merge into a sea of neutrons threaded with superconducting currents. In this environment, the star's rotation doesn't just spin its spirals into overdrive, as if the star knows its time is limited and refuses to go quietly. The real magnetic magic happens in the star's fleeting stability. Supermassive neutron stars often rotate at breakneck speeds, their centrifugal force helping them stave off collapse. This rapid spin, combined with their absurd density, turns their interiors into dynamos of unbelievable power. Differential rotation, where the star's outer layers whirl faster than its core, becomes a runaway process, twisting magnetic field lines into braids of pure energy. Picture a tornado made of lightning, then imagine that tornado is the size of a city and spinning 1,000 times per second. That's the kind of magnetic turbulence we're talking about. But here's the twist: these stars aren't built to last. Without enough mass to become black holes, they're also too massive to remain stable as ordinary neutron stars. Over time, as they lose rotational energy to magnetic braking and gravitational waves, their support system weakens. The moment their spin dips below a critical threshold, poof, collapse becomes inevitable. Yet in their final years or even millennia, these doomed stars might ramp up their magnetic fields to Magnetar levels, as if screaming their existence into the void before vanishing. There's tantalizing evidence for this. Some short gamma-ray bursts, those blinding flashes thought to signal neutron star mergers, are followed by puzzling X-ray plateaus that linger for hours. These could be the death throes of supermassive neutron stars, their magnetic fields shining brightly as they spiral toward collapse. Even more compelling are the missing pulsars in certain supernova remnants. When a star explodes and leaves behind no detectable neutron star, it's possible the remnant was supermassive, briefly flaring as a magnetar before disappearing into a black hole, leaving only a magnetic echo behind. The implications are staggering. If supermassive neutron stars really do forge magnetars, it means some of the universe's most magnetic objects are born from its most unstable ones. They're cosmic mayflies here for a flicker, but burning bright enough to outshine galaxies on their way out. And that raises a haunting question: how many magnetars have we missed because their creators didn't stick around long enough for us to see them? Perhaps magnetars don't form through a single catastrophic event, but through a cascade of them, each amplifying the last until the star crosses a threshold into magnetic madness. This final theory suggests that no single mechanism is enough to create the universe's most magnetic monsters. Instead, magnetars might emerge from a perfect storm of overlapping processes, a multistage amplification where chaos stacks upon chaos, each step pushing the star closer to an extreme no single phenomenon could achieve alone. Picture a massive star collapsing, its core spinning faster as it shrinks. The first stage, a dynamo effect turbocharged by differential rotation. But this alone might only create a strong neutron star. Now imagine that same star formed in a magnetically enriched region of space, its birth shrouded in a nebula threaded with primordial fields stage 2, environmental flux freezing, compressing those external fields into the star's crust like a cosmic press. Even then, it might not be enough. Add a third ingredient, fallback, where chunks of the progenitor star's magnetized corpse rain back onto the neutron star's surface, injecting fresh magnetic energy like a series of high-voltage shocks. Only now, with all three mechanisms working in concert, does the star tip into Magnetar territory. The evidence lies in the outliers magnetars whose properties defy explanation by any one theory. Take SGR 0501 plus 4516, a magnetar with a magnetic field so twisted, its X-ray pulses flicker erratically like a strobe light. Models suggest it couldn't have reached such extremes through dynamo action alone, but factor in its location, an ancient supernova remnant rich in magnetized debris, and suddenly the math aligns. Or consider Swift J1834.9-0846, a magnetar surrounded by a disk of glowing material. Its youth suggests it's too old for a traditional dynamo, but too young for Hall drift to have amplified its fields. Yet if it devoured magnetized fallback material while also harboring a hyperactive core dynamo, the pieces fit. What makes this theory so compelling is its flexibility. It doesn't discard other ideas, it synthesizes them. A neutron star born with moderate spin might not become a magnetar through differential rotation alone, but if that star later gets spun up by accreting material from a companion, or if its crust fractures in just the right way to unleash Hall-driven amplification, the combined effects could bridge the gap. Even quantum vortex alignment, which might seem niche on its own, could play a critical supporting role, stabilizing fields amplified by other means. The implications are profound. If magnetars require this perfect storm of conditions, their rarity isn't just a fluke, it's inevitable. Most neutron stars might experience one or two amplifying mechanisms, but only the unlucky or lucky. Few hit the cosmic jackpot, enduring every stage of magnetic escalation. It also explains why magnetars seem to cluster in certain regions of galaxies like the turbulent, magnetically rich environments near supernova remnants or star-forming hubs, where multiple amplification processes are likely to overlap. Yet the mystery deepens when we ask which combinations are necessary. Could a dynamo plus quark matter transition suffice without fallback? Or does crustal fracturing always need a neutrino kick to push it over the edge? The answers might lie in the outliers, the magnetars that break all the rules, like the recently discovered slow magnetar with a surprisingly weak field but violent flares, or the fast ones that spin rapidly yet still exhibit magnetar-like outbursts. These oddballs could be the key to decoding which amplification stages are essential, and which are just cosmic icing on an already unstable cake. One thing's certain, if multistage amplification is real, it means the universe doesn't just create magnetars, it engineers them, stacking the deck until the star has no choice but to become something monstrous. And that raises a humbling thought. For every magnetar we see, there might be 100 near-misses neutron stars that came almost close enough to crossing the line, but lacked that one final push into the abyss of magnetic extremity. From hypernova birthing magnetic titans to cosmic strings slicing through spacetime, from quantum vortices aligning in eerie unison to neutron stars feasting on magnetized stellar remains, the 30 theories we've explored today reveal just how wildly inventive the universe can be when crafting its most magnetic monsters. Each hypothesis, whether grounded in decades of research or dancing on the edge of speculation, underscores a humbling truth. Magnetars don't just push the boundaries of known physics, they gleefully demolish them. They force us to rewrite the rules of superconductivity, rethink the nature of matter itself, and confront phenomena so extreme they blur the line between astrophysics and quantum sorcery. What's fascinating isn't just the diversity of ideas, it's how many might be simultaneously true. Perhaps magnetars are born from a perfect storm of hyperrotation and quark transitions and fallback accretion, their magnetism sculpted by multiple cosmic sculptors working in tandem. Or maybe there's no single recipe. Different magnetars could arise from different cosmic catastrophes, their shared ferocity masking wildly distinct origin stories. The fact that after decades of study, we're still debating these possibilities speaks to how little we truly grasp about the universe's most volatile laboratories. But here's where you come in. Which theory ignites your imagination? Do you see magnetars as dark matter traps, their cores seething with invisible particles? Or as quantum rebels, where vacuum fluctuations and strange quarks conspire to defy physics as we know it? Maybe you've got a wild idea of your own, some untapped mechanism lurking in the math, waiting to crack the Magnetar code. Drop your thoughts in the comments, debate your favorites, or spin a fresh hypothesis into the mix. After all, the next great theory might not come from a lab or telescope. It could start right here in the collision of curious minds. And while you're at it, hit that subscribe button if you haven't already, because the Magnetar mystery is far from solved, and when the next breakthrough cracks open the cosmos's magnetic playbook, you won't want to miss it. Until then, keep looking up, and remember, the universe's most terrifying monsters are also its greatest teachers. Who knows what they'll force us to learn